right, here we are, Unit 5, Lesson 2. We are going to talk about the solutions to linear inequalities. Last time we graphed them, and this time we're gonna graph them, but we're also gonna talk about what the solutions are and what they mean. All right, so an inequality has many solutions. The solutions are the ordered pairs. Okay, remember an ordered pair is x, comma, y. An ordered pair is a location. Okay, it tells you where that point is located. Has an x value and a y value. So it's the ordered pairs in the shaded region. Points on the line are only solutions if the inequality is less than or equal to or greater than or equal to. Okay, in other words, points on the line are only solutions if the line is solid. If the line is a dotted line, then points on the line are not solutions. All right, so take a look at this one. So y is greater than or equal to 2x minus 4. So my m is 2 and my b is negative 4. So I need to graph the border line or the boundary line first. So I'm going to start at negative 4. All right, so I'm going to go, let's see, 1, 2, 3, 4. And I'm going to go up 2 over 1, up 2 over 1, up 2 over 1, 2 over 1, oopsie, that guy, up 2 over 1. All right, that's good there, down 2 over 1. Okay, that's good enough. All right, so now I need to draw my boundary line. Well, my boundary line is going to be solid because of that equal to. So let me get my solid line here. Remember, your line needs to go through the coordinate plane. All right, so there is my boundary line. So now I need to shade. Where am I going to shade? Greater than, I'm going to shade above. Okay, so I'm going to go to my y-intercept and I'm going to go up. So this is the side that I'm going to shade. So all of this shaded region represents solutions to this inequality. Now, let's talk about exactly what we mean by that. Okay, so it says give 3 examples of solutions to the inequality above. So here's one example of a solution. How do I know that's a solution? Because it's clearly in the shaded region. What is that point? 1, 2, 3, 4. That's negative 4 for the x and 2 for the y. So negative 4, 2 is one example of a solution to this inequality. All right, let's find another one. Okay, what about this guy right here? That's negative 4, negative 1, 2, 3, 4, 5, 6. Negative 4, negative 6. So I'll write these down here for y'all. Negative 4, 2, negative 4, negative 6. And then let's go up here. What about this guy right here? 1, 2, 1, 2, let's see, 1, 2, 3, 4. So 2, comma 4. So all 3 of those are solutions to this inequality. All right. Now what about points that are not solutions? Give 3 examples of points that aren't solutions. Okay, so I'm going to do that in red. This is not a solution because it is not in the shaded region. So that's 1, 2, 3, 4, 5, negative 1, 2, 3, 5, negative 3. And I'm going to let you do the others. Okay, anything in this area is not going to be a solution. All right, so then it says, is 12, negative 8 a solution? Okay, so where is the point 12, negative 8? Well, here's 10, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 10, so if I go 11, 12, I'm off the graph obviously, and down to negative 8. Okay, what do you think? That's probably not a solution. Okay, this line goes down this way. Okay, so anything above the line is a solution, anything below it is not. Okay, so that is not going to be a solution. And what we're going to do is we are going to do this algebraically because sometimes your points are going to be off the graph and you may not know exactly where it will be. Now this one seems pretty obvious, okay, because negative 8 is literally like right here. So it's clearly not in the shaded region. But I'm going to show you how to do that algebraically also. Now remember, that points on this line are solutions. Let me go back and add one more here. So for example, this point right here is on the line. That is a solution. So that's 1, 2, 3, 2. So 3, 2 is a solution because it's on the line and the line is solid. Why is the line solid? Because of the equal to. All right, so now we're going to solve these inequalities algebraically and see if they are solutions. So it says, given y is greater than or equal to 2x minus 4, identify if 12 negative 8 is the solution. Okay, so that's the one we just did. So let's do this algebraically. Now remember, this is an ordered pair. This is x and this is y. So all I'm going to do is I'm going to plug these in for their respective variables and see if it's true. All right, so for y, I'm going to plug in a negative 8 is greater than or equal to 2 times 12, because x is 12, minus 4. So all I did was plug in the x value for x and the y value for y. Now I'm going to do the math. Negative 8 is greater than or equal to 2 times 12 is 24, minus 4. Okay, so what is that? Negative 8 is greater than or equal to 20. Is that a true statement? Is negative 8 greater than or equal to 20? No, it is not a true statement, therefore that is not a solution. This has to be true in order for this to be a solution. All right, let's look at this next example. So this one is in standard form, but it doesn't matter what form it is if you have the ordered pair and you're trying to find if it's a solution. I'm still going to plug in this guy for x and this guy for y and do the math. Okay, so negative 3 times 8 minus 4 times 4, again, this is x and this is y from here. I'm plugging it in, is greater than 8. All right, let's see if that's true. Negative 3 times 8 is negative 24. Negative 4 times 4 is minus 16, greater than 8. Negative 24 minus 16 is negative 40, right? Is negative 40 greater than 8? No, it is most definitely not. So this is not a solution. All right? All right, so now I want to look at this same inequality, but I want to try a different point. So we're still going to do negative 3x minus 4y is greater than 8. And now we're going to test the point for negative 5. Is that a solution or not? Let's see. So we're going to plug it in. Okay, so I'm going to plug this guy in for x and this guy in for y. So negative 3 times 4 minus 4 times negative 5 is greater than 8. Again, we're testing this. We're trying to see if this is actually true. Negative 3 times 4 is negative 12. Negative 4 times negative 5 is positive 20, greater than 8. Negative 12 plus 20 is 8. So we get 8 is greater than 8. Is that a true statement? No, 8 is not greater than 8. Okay, so that is not a true statement, so this is not a solution. Now, what does this mean here if I get the same number on both sides? This is an indicator that this point is on the line. This point here is on the boundary line of this inequality. If I were to graph this, this point would be on the actual line. And the reason that it's not a solution is because the line would be a dotted line. The line's going to be a dotted line, and therefore that's why this is not a solution, because it's on the line and the line is dotted. Okay? Now, if I would have given you negative 3x minus 4y is greater than or equal to 8, then I would have gotten negative 12 plus 20 is greater than or equal to 8. 8 is greater than or equal to 8. That is true. Okay, so if it would have had the equal to sign, again, this point still would have been on the line, but this time, since it's a solid line, it would be a solution. So you really have to pay attention to that. And you should see from here, you should know that 8 is not bigger than 8. Okay, if I have $8 and you have $8, nobody has more than the other. We have the same amount. So that is not a true statement. All right, so that is all you need to know about solutions. Again, you can identify solutions from a graph, but you can also identify them algebraically by plugging in the ordered pairs. Okay, if you're trying to find solutions, it's probably easiest to graph, but if you're trying to determine if a point is a solution, you're most likely going to want to do that algebraically and save your time in graphing. Remember, you can graph an inequality from standard form. Okay, we did this one from slope-intercept form, but don't forget, just because it's in standard form doesn't mean you can't graph it. All right, great job. We'll see you in class.